CTS without non-default rules, NDR, potential issues and consequences. The question you asked is very insightful. In VLSI design, non-default rules, NDR, are sometimes used during clock tree synthesis, CTS, to provide wider metal traces and increased spacing specifically for clock nets. Let's explore what might happen if NDR isn't used during CTS and the potential consequences in later stages. Challenges during CTS. Increased crosstalk susceptibility. Without NDR's wider traces and increased spacing, clock nets become more susceptible to crosstalk. Crosstalk occurs when the switching activity on one signal can induce unwanted voltage fluctuations on nearby signals, potentially causing timing violations or data corruption. Signal integrity degradation. The standard metal widths and spacings might not be sufficient to ensure optimal signal integrity for the high-frequency clock signal. This can lead to increased signal attenuation, weakening over longer distances, impacting clock arrival times and potentially causing timing violations. Consequences in further stages. Place and route, PNR. During PNR, the router might struggle to efficiently route the clock tree due to the standard metal widths and spacings. This can lead to routing congestion. Difficulty in finding enough space for the clock tree might cause congestion issues, impacting the routability of other signals as well. Delays and skew. Inefficient routing with tight spacings can introduce additional delays and potentially worsen clock skew. Static timing analysis, STA. STA analysis after PNR might reveal timing violations due to increased delays and skew arising from the lack of NDR. This could necessitate further design modifications or optimizations. Physical verification. The router might be forced to resort to undesirable routing techniques, e.g., sharp bends, to accommodate the standard metal widths and spacings. These techniques might require extra scrutiny during physical verification to ensure design rule compliance. Potential mitigation strategies. Careful clock tree planning. Strategically planning the placement of clock buffers during the design stage can help minimize the overall length of clock nets, reducing the impact of standard metal widths and spacings. Cell sizing optimization. Adjusting the sizes of standard cells along critical paths can help improve timing margins and potentially reduce the need for aggressive routing strategies during PNR. Relaxing skew target, if possible, if acceptable from a performance standpoint, relaxing the clock skew target can provide the router with some flexibility during PNR, potentially alleviating congestion issues. Conclusion. While using NDR in CTS isn't always mandatory, its absence can lead to challenges with crosstalk, signal integrity, and routing complexity. These issues might impact routability, delay, skew, and require additional effort during PNR, STA, and physical verification. Careful planning and potentially relaxed skew targets can be strategies to manage these effects. Why use clock buffers instead of normal buffers in CTS? Showing the question. The question you asked is very important. In clock tree synthesis, CTS, clock buffers are the preferred choice over regular buffers for several reasons. Key reasons for clock buffers. Maintaining duty cycle. Clock buffers are specifically designed to have equal rise and fall times. This is crucial for maintaining a proper 50% duty cycle, equal high and low signal duration, for the clock signal. Regular buffers might have slightly different rise and fall times, which can distort the duty cycle over a chain of buffers, potentially causing timing violations in downstream circuits. Minimizing skew. Clock buffers are optimized to have consistent delay characteristics. This helps minimize clock skew, variation in arrival time, across different parts of the design. Regular buffers might exhibit slight variations in delay, leading to increased skew and potential timing issues. Higher drive strength. Clock buffers are typically designed with higher drive strength compared to regular buffers. This allows them to drive the clock signal over longer distances and through larger fanouts, driving many other cells, with minimal signal degradation. A strong clock signal is crucial for reliable operation of sequential circuits, flip-flops. Drawbacks of regular buffers. Unequal rise and fall times. As mentioned earlier, regular buffers might have slightly different rise and fall times. This can cause duty cycle distortion and potentially lead to timing violations. Increased skew. Variations in delay characteristics of regular buffers can contribute to clock skew, making it harder to achieve tight timing constraints. Lower drive strength. Regular buffers might not have sufficient drive strength to handle long clock nets or large fanouts, leading to signal degradation and potential timing issues. Conclusion. While both clock buffers and regular buffers can amplify signals, clock buffers offer distinct advantages in terms of maintaining duty cycle, minimizing skew, and providing higher drive strength. These characteristics are essential for ensuring proper clock signal distribution and reliable operation of sequential circuits in a VLSI design. That's why clock buffers are the preferred choice for building robust clock trees during CTS.